All right, good afternoon, everyone. We're going to have to fix that. Okay. I think we're set up now. Everyone have a nice Labor Day weekend. I did, although I worked all weekend. But all right. Welcome to our second class after a nice long break from the first class. I hope you're all enjoying your first assignment. We like to get you started early in this class. So in our second session today, I'm going to start with a fairly lengthy review of our first session, just because it's been a couple weeks and I want to ease everyone into the class. So we're going to go over all the stuff that we went over last time a little bit quicker and make time for some more coverage of different plots of univariate data, and also get into some numeric summaries for center and spread, which probably most of you have covered before, so it'll be another bit of a review class from times before, but we'll also introduce some terminology and just bring you into the context of this class. So as it turned out, I discovered that Google Chrome was not installed on this machine, so I'm having to do the broadcast from my laptop, which is why there's a little bit of delay here. But on the bright side, what you see on the screen is exactly what you will see if you watch the video again later from home, or if for the people who are tuning in live right now. So just to review the vocabulary that we learned last time, the population in the context of statistics is an entire group of interest. It might actually be people, but it might be other things like lab tests or results of a lab test. It is all of the possible things, items, or records that we are interested in. And it's something that normally we can't observe all of, so we take a sample from that population, which is a subset, and something that we can practically measure or observe in our study. Again, those records are observations. Each of those is the data from one individual or observation. And we sort of split statistics into a few different categories. There was descriptive statistics, which is the qualitative and graphical descriptions of things. Statistics, which is making inference about the population from our sample. Hi, Tony. And the one I didn't put in here, but we did mention last time, was experimental design, which is everything that you do before you start your study. Oops. So we learned about a few kinds of variables, which is any characteristic or thing that is recorded for the subjects in the study. And we covered nominal variables, including binary, which has 2 levels, categorical, which has 3 or more levels, ordinal data, which is a special type of categorical data that has a natural ordering to it, and quantitative data, which includes both discrete and continuous data. Discrete meaning that it takes on only particular values, and continuous, of course, meaning it can take all possible values between the bounds. Oops. Need to put away that keyboard so I stop pressing it. We learned for the nominal and ordinal data that you could use frequency tables or contingency tables, which is just a table listing the number of counts or percentages for each of the categorical possible values of the variable, and bar plots, which is a graphical summary of the same things. Those are descriptive descriptions, well, numerical descriptions of categorical variables. I think I told you that we statisticians don't like pie charts unless they're made of actual pies. Pie charts are not very quantitative. They use up a lot of space without making it very easy to actually read numbers or quantitative information off of the chart. So it's just an inefficient use of space. And generally anything that you could visualize using a pie chart, you can also visualize using a bar chart such as this, which is not as interesting, although it's possible to spruce up your bar charts a little bit. But unless there's this special case like the actual pie, I'd recommend that you stick with bar charts and some of the other things that we cover, such as tables. For the nominal and ordinal data, all of these different summary measures. So I mentioned that the frequency or contingency tables, you could put actual counts. Alternatively, you can put proportions, frequencies in there, and percentages. And actually often the so-called epidemiological table 1 will have both of these. It'll have the actual counts, and then it'll have percentages. And you can use any of those actual counts or proportions or percentages for a bar plot. For quantitative variables, that is the discrete and continuous type, but where the rules of mathematics hold and it means something for one number to be twice as big as a number as another, for example. There are a bunch of different graphical summaries of these. We covered the dot plot, which is just where you have one dot there for each observations. A histogram, where you categorize your continuous data and turn it into ordinal data and plot those ordinal data as a histogram in the order of the magnitudes represented by each bar. And then the box plot, which has both some qualitative and quantitative measures together, which is one of my favorite plots. But all of these help you identify key attributes of a continuous variable, such as the central tendency, where the middle of the data are, spread, skew, and outliers. And I'll be talking more about all of those and giving examples of how you identify them and analyze these plots. So out of those three, the dot plot shows the most detailed information. It's the least amount of summarization because you see every single data point. And a nice way to make these is they're actually like a histogram. So this is really a histogram, but showing individual data points. The histogram is sort of the next level of summarization, where depending on the width of the bins that you create, you're not showing all of the data, but you're still, it's very similar to the dot plot on the previous page. you're just making the height of the bar show the number of observations in each of these ranges, rather than showing actual data points. So this is still quite a bit of fairly detailed information about your variable, but the level of detail can be tuned in a histogram, and any program that you use to make histograms will offer you an option to set the width of those bins. So there will be a default. It'll try to choose something for you automatically, but hopefully that default is good, because it really affects how you see your data. So in this example, on the right is the most amount of summarization, and you have, and it kind of makes this particular data set of weights of people look right skewed with the most summarization. It looks a little bit different in the middle one, where there's a little bit more detail shown. You see that it does drop off at the low weights, and you kind of see on the left that there's just a couple of almost outlier weights in there that are more common weights. So you can have a different impression of your data depending on how a histogram is summarized, and if you're relying on it to get a feeling for your data, it's not a bad idea to just try a couple of different widths of your histogram. So when you're interpreting these histograms, I mentioned we did a little bit there of looking at the shape, just talking about how the one on the right sort of looked more skewed, that is not symmetric. But the main things we'll look at are center, spread, and shape. The center is I'm leaving it intentionally vague here to mean something like the middle of the data, and there are different ideas of what that means. The centering can mean median, mean, etc. You can assess the spread of the distribution, again being a little bit vague here, but just to mean the general idea of how much did the data vary around that center, and shape as in skew. A symmetric distribution is one that is a mirror image. There's a point in the middle whereby if you are looking at, this would be a probability distribution of a continuous variable. If you put a line in the middle of the graph, then the left and the right hand side of that line are mirror images. Whereas a distribution with a skew is not a mirror image. It will go further out from one side than the other. There's nowhere that you can place that line where you'll get a mirror image, and if you place that line in something like the center of the distribution, in a left skewed distribution, you'll just see a longer tail going out to the left, and in a right tail distribution, you will see the other skew over towards the right. And these come up a lot, skewed distributions. A couple of the classic examples are lifespan. So if you talk about how old people live, in many populations, not all, but you will have a few people who die at young ages, and then increasing amounts as the disease burden adds up, and then a peak where a typical person dies of old age, and then a fairly rapid drop-off after that, reflecting that most people do not live too far beyond that typical lifespan. Income, on the other hand, in capitalist countries anyways, follows a right skewed distribution where you have lots of people with a little income and then a very, very long tail with your Facebook CEOs earning way than anyone else. Now, the central tendency, I mentioned there are some different ways to think about it. If you have a unimodal distribution like this one on the left here, it's pretty clear what you mean by the central tendency. If you have a multimodal distribution such as this bimodal distribution on the right, then it's a little bit less obvious what you mean by central tendency. Any suggestions as to when a multimodal variable might come up in practice? It does come up. I can't think of one off the top of my head, which is why I'm asking you, but there are lots. Yeah.
That like this, there's two types, type 1 and type 2. Type 1 is predominantly in the early age.
Sorry, two types of what?
Diabetes.
Diabetes, okay.
Yeah, diabetes. So type 1 is predominantly in the early age, and type 2 is in the mid-40s to 50s.
Okay, so
So
if you had a population of diabetes patients and you just recorded the ages of all of them, you would see a bimodal distribution with, although the sufferers of type 1 diabetes would still have it at an older age. So I guess if you were looking at age of onset,
yeah,
right? Yeah. So age of onset of diabetes would be a bimodal distribution, leading to the name type 1 and type 2, from which mode it belongs to. Good example. An outlier is an observation that falls a long ways away from the rest of the data. And what do I mean by a long ways away from the rest of the data? Well, there are lots of definitions of that, and there isn't really a standard definition of an outlier. It's just something that you think is not typical of your data set, and you think might represent something different. It was generated in some other way than the rest of your observations. So you can look at a plot like this and see something over on the right, and down here at the 100, there's one observation that is quite a ways away from all the rest, and say this looks like an outlier. Now, sometimes an outlier can be caused by an error, or by, in some cases, people collecting and recording data will record something as a 99 when everything else is in the 0 to 5 range or something. And in a case like that, the number 99 doesn't actually mean anything. And so, but if you plotted them all, you might see it appear something like this. And when you see an outlier, the idea is just to give a little bit of extra attention to that point and try to see if you understand why it's an outlier. Because in some cases, there's nothing wrong with the data, and it just happens that in your probability distribution for this variable includes some points that are far away from the center and beyond the normal spread. In other cases, it's a sign of something wrong. So for this reason, you need to think twice about whether to remove an outlier or not. It's generally not justifiable just to see it and remove it. You should have a reason for removing it. Yes.
Is like you, like, let's say your data is supposed to be between 0 and 5, and there's 99, and it's maybe it's wrong with human error, like
So it's data that are supposed to be between 0 and 5, like a scale or something.
Yeah.
Yeah, I mean, in that case, it's easy. If it's a scale between 0 and 5 and you see a 99, well.
But if you like, you think that it is a typo or something.
Sure, like if we're talking like you know, weights of humans and you see 1,000 pounds or something, you're like, okay, that's not a real value. But you know, if you see a weight of 300 pounds in a data set that of mostly skinny people, maybe that's a real weight. So I mean, you might still justify it even if you think that it is a real value, but you decide that you know, the population that you want to study does not include this observation. You can still justify it. The point is just that you should be able to tell someone why you're doing it. And usually that would be a part of your methods. If you're writing up an analysis, you would say values beyond this range were excluded because something like this. So the box plot is a wonderful plot that I never learned about until after my PhD, but now I couldn't live without it. It's a wonderful plot because it's both qualitative and quantitative. You can just take a look at it and immediately see where the center of the distribution is, a couple measures of its spread. You can see its skew, but you can also tell a number of quantitative things about the distribution. So the key points of the box plot are the line in the middle. This is the median. The boxes go out to the first and the third quartiles, so the 25th and 75th percentiles. And from those first and third quartiles, the whiskers extend out to 1.5 times the interquartile range. The interquartile range being the width of the box. So let's see, that's the width of the box. 1. So this is a little bit less than half maybe, and the reason for that is that if there's no data point out as far as 1.5 times the IQR, then the whisker will not go out that far. It will only go as far as the furthest data point. And then anything that lies outside of that whisker, that is one definition of an outlier. That's just something that is quite a ways away from the center. This is actually a good, yes. Yes, so the whisker extends from the outside of the box for another 1.5 times the interquartile range, but only if there is a data point at least that far. If there's no data point as far as 1.5 times the interquartile range, then the whisker will only go as far as the furthest data point. And any data point outside here, that is one way of identifying possible outliers. But this is a good example of how just because something meets a definition like this of an outlier doesn't mean there's anything even unusual or unexpected about the data point. So this is an example drawn from a normal distribution. So I actually simulated these data. I did it myself. I know that the data from which I drew this probability distribution and drew this box plot came from a perfect normal distribution. Now, you know anything about a normal distribution? We will cover it, so you don't have to know about the normal distribution yet. I won't assume anything, but a normal distribution, basically, it's the bell curve. It looks like this. A peak in the center, and it comes out in the shape of a bell in both directions. So the most likely value for any particular observation is right in the middle, and the further away you get, the less likely it is that you will observe that in any given observation. But the more and more observations you draw, so the bigger your sample is, what are you going to start observing? So let's say we go up to 10 observations, 100, 1,000. What's the likelihood that you observe some, get one measurement way out here? Yeah, it gets more and more likely the more and more data that you draw from this normal distribution. So in fact, if you have even say 1,000 observations from this normal distribution, almost certainly you're going to have some data points outside these whiskers that look like so-called outliers. So if you were to just go and remove them, you would no longer have a normal distribution because you've just cut the tails off of your normal distribution. So so any distribution that has a tail to it, the more observations you have, the more so-called outliers you're going to see if it's just a rigid definition like this one. Let's see, I'm just going to double check that our online folks can look at this. All of this is appearing right there in Blackboard. Isn't that amazing? Ah, test scores. Sure, I guess test scores could be a bimodal distribution. Maybe if you had like elementary students and college students taking a math test, something like this. I wonder if there's a way I can set this so that I can actually see the chat at the same time. Not that I know of. Oh yeah, there we go. I don't know, now you're not seeing the bottom of the slide though. Okay, we'll go back to regular viewing mode. One of the nice things about box plots as opposed to histograms or dot plots is it makes it easy to compare multiple distributions side by side. You can put them together in a box plot, and each variable that you put there just has its own box. So it becomes then very easy to compare two variables like the heights of males and females and immediately see that the center or the median height of males in these observations is higher, and that there is some overlap in those distributions. You can see that their middle interquartile ranges do not overlap, but the tails of the distributions certainly do. So it's a very good, both for the quantitative attributes of being able to read some things off it and the qualitative attributes of being able to just compare distributions side by side. Yes?
change the x-axis with y-axis, exchange them? Here in this
Oh,
example?
yes. So that in that example, that was a horizontal box plot with horizontal boxes. It is actually more common to do it the other way, like you say, with vertical boxes. I know in R you can just choose, it's just an option, vertical or horizontal. I think you can do the same in SPSS, but it's really depends on I don't know, on your labels. Like if you have long labels of the variables, maybe it's easier to put it horizontally. But yeah, it's equally valid either way. More common to put them vertical. Let's talk about some numerical summaries. So we've already covered a few of these just in the discussion of the plots, but I want to talk about these numerical summaries of central tendency, spread, and distributions. So the mean, the one I mentioned as having its roots some 4,000 years ago. The delay is getting a little longer here. There we go. It's just the sum of the observations divided by the number of observations, or using this so-called capital sigma notation that annotates sums, it's the sum from the first observation to the last or the nth observation of all of the observed values, x sub I. We call that x bar. Remember in the syllabus, I gave you a summary of statistical notation. So you'll see in there that that we tend to use the lowercase Roman letters to denote observed values, uppercase ones to annotate random variables, Roman for samples and observations, and Greek letters for population parameters. Let's see, I'm going to call up our the PowerPoint on the screen here because I'm tired of waiting for these. Okay. One thing you should know about the mean, it's incredibly useful and we use it all the time, but it's not resistant to outliers or to skew. It's strongly influenced by them. So I've drawn here 4 different distributions. On the left, a normal distribution. The second one is a so-called log normal distribution. This is one where if you take the logarithm of it, you get a normal distribution. An exponential distribution. So this is an exponent of a uniform distribution. And then on the right, a uniform distribution between -1 and 1. And on each of these, I've drawn a box plot. And these boxes, I'm showing all of the data points and putting a little bit of jitter on them so that they're not right on top of each other. And then I've overlaid here the mean. So you remember that the middle bar on a box plot is the median, but I've just overlaid the mean here. So what do you notice about the normal and the log normal distributions when you're comparing the median and the mean? Yep.
very different.
Yeah, well, in the normal distribution, they're pretty well the same. They're almost exactly the same. But in this log normal distribution, which is extremely skewed, yeah, they look,
Because of the outliers.
yeah, because of the outliers and because of the skew. In fact, technically these are not outliers because they are a part of the distribution. It's just an extremely skewed distribution. So the mean is affected by outliers and it is affected by skew. And in fact, from only numeric summaries of the data, if you see the mean and the median, if they're very different, you can infer that it must be a skewed distribution or it must have outliers. Because if it's a symmetric distribution without outliers, they'll be very nearly the same. So the exponential distribution is skewed, but not as much. And we see a smaller difference between the median and the mean. And then the uniform distribution is not skewed and it has no outliers. So again, they're almost the same. They're not quite the same. Do you know why they're not quite the same here? What's that?
The box is not divided symmetrically in
Yeah.
uniform.
That's true. This box is not divided symmetrically. Why is that? Skewed, outliers. This is a uniform distribution. I promised that I generated this from a true uniform distribution, meaning that observations have exactly the same probability of being anywhere between -1 and 1. What about 0? No, it doesn't. This is a really important point, actually. I'm glad that we've stopped here because you're going to get data, you're going to plot it, and you're going to spend so much time looking at this and trying to understand the variables in your data set by looking at your sample. But look at this. I know what these distributions are, exactly what they are, and yet it doesn't quite match my expectations. Yeah? Exactly, it's randomness. These data points that you see here represent a random sample from these 4 distributions. So when you take a random sample, you have sampling variation. It would be possible, not very likely, but for these, I think this is 100 data points, for them all to be positive, even though there was equal probability of them being between -1 and 1. That's not what happened, but by the fact that the median is down a little bit, I can't quite see where the 0 is here, but assuming that the median is negative, it means that we did have a few more negative values than positive ones. So just remember that all you're ever going to get to see of your population is a little random sample, and that little random sample is going to vary from the population properties. And if you take another little random sample, you're going to see something different. And that's why here the mean and the median don't quite match up. For the theoretical distribution, the mean and the median are both 0 for this uniform distribution between -1 and 1. And if we took a big enough sample, let's say 1 million points, then those red and black lines would be almost right on top of each other, but it's not such a big sample. Yes?
Are there, so picture, but are there ways to tell if that is statistically significant?
If,
The mean and the median?
I don't know about to say whether the mean and the median are statistically significantly different, but there are certainly tests to say whether a sample is drawn from a normal distribution, certain things like this, or to say things about the mean. In fact, the z-test and the t-test that you're going to learn are about the mean of a sample. Yes?
So, you say that if the sample size is smaller, there are more chances that the gradient would be different. But if you have a larger sample size,
Yes.
there is more probability, more chances that
this is a really key concept that I'm going to hammer in when we get to the central limit theorem. But this is a really key concept that a small sample is quite variable in its mean, and a big sample has very little variability. So the smaller your sample, the more properties like the mean or anything else that you measure about it, the more it's going to vary if you were to repeat your study and take another sample.
this is the case for uniform study. But if the sample size, on the other hand, if it's normal, then whatever the case is, whatever the sample size is, it will have the same meaning or would be different.
So this, I mean, this is a very general. It's a very general principle that sampling variability is greater for a small sample than it is for a big sample. It doesn't matter what distribution it is, whether it's normal or uniform or log normal or anything. That's a very general property of sampling and so-called sampling distributions. Well, I won't get into exactly what sampling distributions are yet, but just to bring this back to real life, imagine you're talking about something like height. If we were to take any one person in this class, your heights vary quite a bit. If we were to take the average height of everyone in this class and compare that to the average height of any other class in New York City, it's not going to be very different, unless it's like a basketball class or something. But yeah, and that does not matter what distribution it is. Is there another question? Excellent questions. So the mean, remember, was a sum of values divided by the number of observations. The median is just the midpoint or the number of observations, or the midpoint or the 50th percentile. There are different ways of calculating the median. If it's odd, it's easy. If it's even, there are different approaches to calculating the median. This is one way to do it, the average of the two middle observations. But curiously, SPSS does it one way. R gives you about 7 different ways to calculate the median. And one of you can even choose. I think there are ones to say I want it to give me the same answer as SPSS, because there are actually a lot of ways to calculate the median for even numbers of observations. If you have a lot of observations, they're all almost the same. If you have like 4 observations, then they can actually be kind of different. This is the simplest way to do it if you're doing it on your own in an assignment. I always, when I'm writing exams for this course, make it so that the tolerance on a question about this is such that it doesn't matter which method that you choose, just because different software will give you slightly different medians. So a few examples here just to drive in the point that it is resistant to outliers. is that a sequence of 5 numbers, 1, 2, 3, 4, 5, the median is 3. If you replace that last number with 100 million, the median is still 3. So an outlier at the end makes no difference whatsoever. With 1, 2, 3, 4, the median, I think in this case, by any of the methods would be 2.5. It's in this middle one with an outlier. If you got rid of the 1 and just had 2, 3, 4, 100 million, then different software would give you different results for the median. And to keep it real here, here's the median height of the 7 dwarves. And the point here is that it is an actual dwarf. So it's not just, it's not an imaginary value. You can have a mean that is not anyone's weight. And by some definitions of median, it is always an individual observation. And you put in an outlier like this, I don't know, I estimated that median is still somewhere right there in the middle. Okay, no more funny slides today. Yeah.
It's not going to be actual individual the samples even.
It depends on the definition. There are some definitions that will ensure that the median is always an individual. It would choose one of those two, whichever one is closer to the mean, I believe, would be one approach to it. So, but no, in general, the median is not guaranteed to be an individual. Okay, back to seriousness. The mode's the value that occurs most often with a categorical variable. So you can only calculate the mode when you have discrete values, as in a categorical variable. If it's a continuous or discrete variable, then there has to be some kind of, or if it's a continuous variable, there has to be some discretization, like into a histogram, in order to calculate the mode. Just to give a caveat here, in this plot, the mode looks like it is about 13, or it's the bar between 12 and 13. If we changed the width of these bars, then that mode can change, and it might not even be in the same place, because if you had another region with more even bars, then when you group them together, you can get a more frequent category than we had on the left. Does that make sense? So yeah, this bar is surrounded by some short ones. If this bar was surrounded by equal-sized ones, that as we make the bars wider, the mode might actually shift to over here. So it's only a really definite thing for categorical variables. And just to drive this point home, how the central tendency can appear in different places depending on skewness, and the difference between where they appear is even a measure of skewness. So if we have if I tell you that the mode in a histogram is here, the median is somewhat greater than that, and the mean is even greater than that, then even if I don't show you anything about the distribution, I only tell you what the mode and the mean are, you should be able to tell me whether that is a right skewed or a left skewed distribution. Got that? Remember that. I might ask you about that. percentiles. I've been talking about them all class, but just so you actually have a slide and a picture of them. The percentile is that value p for which p% of all of the observed values or values in the population fall below that. So the 90th percentile on a test is the value below which 90% of the students scored. And quartiles are those special percentiles just at 25, 50, and 75. The range is one way to measure the spread of a variable. It's just the difference between the maximum and the minimum values. So I talked about how the median was resistant to outliers. It's a robust measure. Mean is not. What about range? What's that? Not resistant. Yeah. It's not resistant, it's not robust. In fact, it's far more sensitive to outliers than the mean is. It's an extremely sensitive measure to outliers. Generally, you should be careful about interpreting anything from the minimum, maximum, or the range because they are so sensitive to outliers. And if you take another sample, the minimum, the maximum, and the range will probably be quite different from the value you had in another sample. So another way of saying that is if you do a study and you report the range or the maximum, that's probably not a very replicable result because anyone else who does the same study is probably going to get a quite different value for any of those things. And unlike the mean or the median, it doesn't stabilize as you get to larger samples. Actually, what's going to happen to the range if, say, we have a normally distributed population, what happens to the range as you take larger and larger samples? Just, yeah, it gets larger. So it's not even representative of the population. It's really something just representative of your sample. So it might be useful in describing your sample, but it's certainly not a generalizable thing. So in this example, the range is just the maximum 250 minus the minimum of 100, so the range is 150. Variance is a measure of spread, and standard deviation is the square root of the variance. And all this is for each observation, it is the deviation of that observation from the mean. So that's this x sub I minus x bar. It's the deviation of each observation from the mean. There we go. Summed over all the observations. And then I'm dividing here by n minus 1, which is a little bit of a tricky thing, because when we did mean, it was just divided by n. So it's not quite the average squared deviation. If our data come from a sample, that's how we do it. If for some instance we actually had the entire population, or if this mean were just estimated from the population or known from the population, then it would just be divided by n. What would happen to our estimate of the variability when all this is estimated from a sample like this if we just divided by n? Would our estimate of the variability be too high or too low? Or just right? Too low. Why is that? Yes. Okay. But suppose I hadn't shown you this formula yet. I just so in one instance, you know what the true mean from the entire population is. Oh. Okay. And you're using that mean to calculate these deviances. Then instead of using that true mean, I estimate the mean from my sample. And let's say this is a small sample, there are only like 3 observations. So it'll really make a difference. So in the one case, say we're talking about height of the population, and I know the mean height in the entire population. In the second case, I'm just estimating the mean height from these 3 people in my sample. What's that going to do to my estimate of the variance without looking at the formula? So in example one, where the mean comes from the population, I'm saying, okay, the population average height is 5'6", and calculating the deviances from that. In example 2, I take the mean of my 3 samples and calculate the deviances from that.
More chances that small sample size of the distribution.
Yeah, so that is one thing for sure, that you'll have sampling variation in that calculation of the mean. The thing that happens there is that when you estimate that mean from your sample, you're picking the middle value from those 3 people. So in fact, you're picking the place, the mean, that minimizes the deviances, right? You're picking the very, very best value for this X bar to make these deviances as small as possible. So you're going to underestimate your deviance. That is one way to think of why you divide by a smaller number, so you make it a little bit bigger. Let's not talk about confidence intervals yet. Yes. Why is it -1? In a qualitative explanation that doesn't involve a derivation, that is the number of degrees of freedom involved in the calculation of this variance. And it's because we've used 1 degree of freedom of our data set in estimating the mean. That's the best qualitative explanation of it that I know. It's that you're dividing not by the number, but by the degrees of freedom. Yes?
Sorry, so if taking the mean, like you're saying, underemphasize it, just -1 overemphasize it?
No, dividing by -1 gives you an unbiased estimate. It actually, with this formula, if you repeat it over and over, you'll get different estimates of the variance every time, but then on average it will be exactly the same as the correct value from the population. Yes?
You kind of answered it, but it's basically accounting for the fact that it's a sample.
It's accounting for the fact that it's a sample, exactly. Yeah, it's accounting for the fact, it's accounting for the fact that we estimated this mean from the sample, and because we did that, we picked the mean that would minimize the variance, and so the variance is going to be biased to being too small if we don't make some correction. Just to make it a little more real of what these deviances look like and why they're sensitive to skew and outliers, I have actually here plotted what I know to be the true theoretical mean as a horizontal bar for each of these 4 distributions, and then put little red lines from that theoretical mean to each of the actual observations. So these red lines represent the xi minus x bar. X bar is this horizontal line, xi are the observations, and the length of the red line is the deviance. So in the normal distribution, you see, you know, nothing too outlandish. You see some small ones, you see some big ones, and you see everything in between. Remember that super skewed log normal distribution? Those large values are really way, way bigger than the small ones. So you can kind of see that, you know, in the normal distribution, most of them make some significant contribution if you're just adding these up. Actually, these are just the deviances. Let me plot now the squares of the deviances, and here is where you really see how the skew affects things. So now, this log normal distribution, those large values really, really dominate everything that is small. So this squaring of things just exacerbates any effect that an outlier might have. So that was my point here. And the other point is that all of the deviances are positive, which is how the calculation of variance always comes out to be positive. Standard deviation, as I mentioned, is just the square root of the variance. Key point about it is that it has the same units as the observed variable. If the observed variable is in inches, standard deviation is in inches. And it measures the spread of the data. It's never zero unless all of your observations have exactly the same value. If there's any variability in your observations, then it's going to be greater than zero. And the more variability there is, the greater S is, which is, once again, not resistant to skew or outliers. One more look at these box plots. Here I'm plotting not only the mean, but I'm also putting the mean plus or minus 1 and 2 standard deviations, just to show how, you know, in this log normal distribution, yes, the mean got shifted, but the mean plus 1 and 2 standard deviations really shift a lot and are affected by these outliers. So in the normal distribution, they're kind of in the same place as where the boxes are. I think that's why the whiskers ended up being placed at 1.5 times the interquartile range, because that's about where the mean plus 2 standard deviations is in a normal distribution. There are some alternative measures of spread that are robust or resistant to outliers, and in certain instances, these might be more called for. The interquartile range, which I mentioned, is not affected at all by outliers. The so-called median absolute deviation, or MAD, which is sort of an equivalent of standard deviation, but just using the medians. So the deviance from the median and the median amount of that. And the range, which, as I mentioned, not robust at all. This is just a summary I wanted to put up before I call it a day, so that you know on one slide everything that we covered in this class, and that you should make sure that you know going forward and as you go eventually into the exam. And also your learning summary of all of these. And I will try to keep in mind what I think that you should have learned from this session. Any questions before we take a little break and go on to the lab? All right, should we take 5 minutes and Tony can get set up?